lectures on control systems laboratory. In this video, we will see the digital simulation of step response of a type 1 unity feedback second order systems. Coming to the title, digital simulation of a step response of type 1 unity feedback second order systems. It is in second order system type 1. So for that system, we are giving step signal as the input and we need to identify the output response. Coming to the aim, obtain the step response of a unity feedback type 1 second order system with an open loop transfer function g of s equal to 100 by s square plus 10s by MATLAB simulation. If we observe the open loop transfer function, g of s equal to 100 by s square plus 10s. So here the highest power of the denominator term is 2s square. So it is a second order system. Highest power is 2. So that's it is a second order system. And also if we observe the number of poles at origin, here we are having a one pole at origin. Here we are having a one pole at origin. That's why it is called as a type 1 system. So this is a type 1 second order system. For this system, now we are adding a unity feedback and we are applying a step input and we will find the output response. Right. The same way coming to the second case, obtain the step response of a unity feedback system type 1 second order system with the open loop transfer function of one more transfer function we are taking 100 by s square plus 20s. So this one also second order system type 1 system. In the same way one more we are taking g of s equal to 100 by s square plus 100s. Right, all the three will be the second order type 1 systems. Now for that systems we are applying a step input and we will see the output responses and we need to analyze the whatever the transient parameters, that is the transient response analysis parameters. That means the rise time we need to check, peak time, peak overshoot, settling time, and also steady state parameter. Whatever the steady state output we are cross checking, and comparatively we will observe the whatever the damping ratio, what is the effect of damping. If the damping ratio is different, means whatever the changes is there. The damping ratio is changing, means whatever the rise time and whatever the overshoot, and which one is the better one. We'll observe this all details in this video. So first it is in simulation expense. So first we need to calculate the theoretical values, and the same thing we will check in simulation part. So this is the open loop transfer function is there. For this open loop transfer function, if we apply a unity feedback, then we are getting the closed loop transfer function. We are getting the closed loop transfer function. So closed loop transfer function for the first case. Closed loop transfer function for the first case. This is the closed loop system we are having. System 1 equal to 100 by s square plus 10s plus 100. This is the closed loop transfer function. And now we are comparing this closed loop transfer function with the standard form of the second order system. The standard form of the second order system is nothing but omega n square by s square plus 2 zeta omega ns plus omega n square. This is the closed loop transfer function. Now we are comparing this denominator part with our closed loop transfer function. From this we are getting omega n square equal to 100. From the directly omega n is 10. And here 2 zeta omega n equal to 10. And already we know that omega n is 10. If we substitute, then we are getting zeta as a 0.5. That means zeta is 0.5, means it is an underdamped system. So for underdamped system, the output response is exponentially decreasing sinusoidal oscillations. So now we know the zeta value and we know the omega n value. Once if we know the zeta and omega n, then we can identify the transient parameters, transient domain parameters, this time domain parameters, rise time, peak time, settling time, and maximum peak overshoots we can identify. So already here we are having formulas, rise time equal to pi minus tan inverse of root of 1 minus zeta square by zeta by root of 1 minus zeta square. Now if we substitute that zeta and omega n, we are getting rise time as a 0.1639 seconds. In the same way peak time, pi by omega d in terms of omega n means omega n into root of 1 minus zeta square. We know that zeta and omega n, if we substitute, we are getting peak time as a 0.3592. In the same way, we are identifying the settling time, overshoots. Right. Once if we know all this, then transient parameters is over. Then you need to identify the steady state error. How to identify the steady state error means here we are applying a unit step signal as an input. If we are applying a step signal as an input, then the error constant we are getting as a positional error constant Kp. Positional error constant K sub x p. How we are identifying the positional error constant? That is limit s tends to 0, g of s into h of s. But g of s is the open loop transfer function. So here in first case, the open loop transfer function is 100 by s square plus 10s. Now we know the open loop transfer function. We know the feedback element. It is an unity feedback. If we substitute directly, limit s tends to 0, 100 by s square plus 10s. So in place of s, we are substituting 0, then we are getting total denominator will be 0. So anything by 0, we are getting as an infinity. Kp is infinity. If Kp is infinity, if we substitute in the steady state error, that is 1 by 1 plus Kp, that is 1 by infinity, we are getting as a 0. Steady state error is 0. That means final value you are getting as the same as an input 1. This is the first case. In the same way, we need to identify for the second case also. If the second case open loop transfer function is 100 by s square plus 20s is there. If we convert this one into the closed loop, that means if we're adding a unity feedback, then we are getting a closed loop system. And the closed loop system will be 100 by s square plus 20s plus 100. So for the second case also, we need to identify the zeta on omega n. Once if we know the zeta on omega n, there we are getting the critically damped system. That means zeta equal to 1 we are getting. So it is a critically damped system. So for the critically damped system, we need to identify what is the rise time, settling time, overshoots, peak amplitude, peak time. In the same way, we need to identify the steady state error also for the second case. Here the open loop transfer function is 100 by s square plus 20s. So if we substitute limit s tends to 0 g of s into h of s, then we are getting the kp value. Kp is an infinity. So once if we know the kp value, then substitute and identify the steady state error. So we are getting steady state error as a 0. Steady state error as a 0. This is the second case. In the same way, coming to the third case. In the third case, we are taking open loop system as a 100 by s square plus 100s. Here the open loop transfer function is 100 by s square plus 100s. So if we find the closed loop transfer function, we are getting 100 by s square plus 100s plus 100 is the closed loop transfer function. For that also, we need to find the omega n and zeta. So for the third case, we are getting a overdamped system. Greater than 1 will come. So it is an overdamped system. So again, for overdamped system, we need to find rise time, settling time, overshoots, peak amplitude, and peak times. Now, if you observe these three systems, in the first one will be the underdamped system. This one we are having oscillations, exponentially decreasing oscillations. And coming to the second one, it is a critically damped system. Here we're not having any oscillations. In the same way, in third also, we are not having oscillation. That means overshoot will be 0. Overshoot will be 0. And one more thing, if we are increasing the zeta value, what about the rise time? Rise time is increasing. Rise time is increasing. If the rise time is increasing, means the system is slower. Response becomes slowly. That's the main thing. Okay. And coming to the steady state part, in all the three cases, Kp value is infinity. So we are getting steady state error as a 0. All the three cases, all the three programs, steady state error will be 0. The steady state error will be 0 means the final value will be 1. The final value of output when time t tends to infinity is 1. Only output will be 1 we are getting. Right. This is the theoretical calculation part. Once the theoretical calculation is over, now we need to write the programming for this three transfer functions. Okay. Yeah. Coming to the programming part, we need operator circuit is personal computer and MATLAB software. And coming to the block diagram, this is a open loop system. For that, we are adding a unity feedback. Then we will get the closed loop transfer function. For the closed loop transfer function, we are applying a step input. Input is a unit step signal, and then you need to observe what about the output response, that is transient and time, transient and steady state we are observing. So this is the open loop system. First case, what we are taking 100 by s square plus 10s. 100 by s square plus 10s is the open loop system. And if you convert that one into the closed loop, that means if we add a unity feedback, then you are getting the closed loop system. That is 100 by s square plus 10s plus 100 is the closed loop system. The same way coming to the second case. This is the open loop system. If we convert into the closed loop, then you are getting this one after adding a unity feedback. 100 by s square plus 20s plus 100 is the closed loop system. The same way coming to the last case, third case, is the open loop system. If we convert into the closed loop, then we are getting 100 by s square plus 100s plus 100. Right. And now coming to the programming part. First, we need to specify the numerator and denominator of the open loop transfer function. Once if we know the numerator and denominator, then we are framing a transfer function, open loop transfer function. For that, we are giving a unity feedback. And now a combination will give the closed loop transfer function. For the closed loop transfer function, we are applying a step signal as an input, and we need to analyze the output characteristics. That means the numerator part. In numerator, we are having a constant 100. We are not having any steps, so that directly 100 we are placing. And coming to the denominator, here the higher coefficient is S square coefficient is 1. Highest power is S square. And S square coefficient is 1. And next coefficient S power 1. S power 1 coefficient is 10. And what about the next one? S power 0. We are not having S power 0, so we are placing as a 0. This is the numerator and denominator. Once the numerator and denominator is over, and by using these two, we are framing a new transfer function. That is the open loop system. We are assuming SYS system. SYS equal to TF. TF is a predefined function, transfer function of numerator comma denominator. This value will give the open loop system. For that, we need to add a unity feedback. So we are assuming as a H. H is a variable. Anything we can assume. H is equal to 1 unity feedback. And now this two combination. If we add a feedback to the already existing system, that is new transfer function, closed loop transfer function, SYS1 equal to feedback of existing system, comma, unity feedback element will give the closed loop system. For that, we are giving step input and check the analysis part. The same way come into the second program. Second program also same. We need to specify the numerator and denominator of the open loop system, and then we are framing a transfer function, open loop transfer function, and then unity feedback. We are adding unity feedback to the already existing system. Then we are getting the closed loop system. For that system, we are applying the input. So here the coefficients are numerator 100, and coming to the denominator, S square coefficient is 1, S power 1 coefficient is 20, S power 0, we are not having anything, that's why 0. Right, this is the second program. And coming to the last one. The last one is the open loop transfer function. Here the numerator coefficient is 100. And coming to the denominator, S square coefficient. S square coefficient is 1. And S power 1 coefficient. S power 1 coefficient is 100. And S power 0 coefficient. S power 0 coefficient is, we are not having any S power 0. So everything is 0. Now by using these two, we are framing a transfer function, unity feedback element. And the combination of these two will give the closed loop transfer function. For that closed loop transfer function, we are applying a step input, and we'll check the analysis part. Right. This is the programming part. And now we'll open the MATLAB and we'll enter the program in MATLAB script file, and we'll see the characteristics. Yeah, MATLAB is there already. You can enter the program, everything in command window also, but in command window, it will show the output of each and every line separately. And there also, it's not possible to save the program. So we'll enter the script file. Okay, editor came. In that editor, we need to enter the programming part. So the first line will be CLC. Why you are placing CLC means the first line will be CLC means it will clear the command window. Previous data, anything is there in command window, it will clear and it will execute the current program output only. It will show the current program output only in command window. First, coming to the numerator. What is the numerator we are having in the first program? This is the numerator we are having in the first program. We will copy directly. It's the first program copied. We will paste in MATLAB. So first numerator we are having 100, and coming to the denominator 1, 10, 0. That numerator and denominator we are framing as a transfer function, system of transfer function of numerator comma denominator, and feedback element H is equal to 1, and then combination after adding a feedback, we are getting a closed loop transfer function SYS1 equal to feedback of existing system comma feedback element. So for that, we are applying a step input, right? And now we'll run the file. It will also save the file first. Okay, we need to save the file so that it will be same. Now you can check the data in command window. Already graph also came. First we will check the command window, and later we'll see the graph. If we observe the command window, first we enter the numerator as a 100 and denominator as a 1, 10, 0. Then we are getting the open loop transfer function. The open loop transfer function is 100 by S square plus 10S. This is the first case. And we are adding a feedback element H is equal to 1. And we are getting the closed loop transfer function. Here the closed loop transfer function is 100 by S square plus 10S plus 10. Already we calculated the zeta value. It is an underdamped system. So for the underdamped system is exponentially decreasing sinusoidal oscillations. If we observe the waveform also, oscillations is there exponentially decreasing oscillations. Now from this waveform, for this waveform, we need to check them. What about the rise time, delay time, peak overshoot, settling time? So for the right click, go to the characteristics and check the peak response. Yeah, this is the peak response. Now check. Transfer function is SYS1, that is a closed loop system. Peak amplitude 1.16. Overshoot, what is the overshoot? 16.3. Overshoot is 16.3. And the peak time is 0.359 seconds. Peak time is 0.359 seconds. And next we will see the settling time. What is the settling time? Here we have the settling time. Settling time is 0.808 seconds. Settling time is 0.808 seconds. And then rise time. Rise time is the rise time. So rise time is 0.164 seconds. Rise time is 0.164 seconds. And we will see the final value. Yeah, this is the final value, which final value is 1. If you observe the previous experiment, that is the type 0 system. If you observe the type 0 system, there we are having a steady state error 0.5 and final value also 0.5. But here, a steady state error is 0. So we are applying unit step signal by getting same as 1 only output. This is the final value. When time t tends to infinity, steady state output equal to 1. So this is the first program output. Right. We will see the next program. Okay, next program also directly we can copy from the slide. So this is the data what we entered in the slide. The same thing we are copying. We are opening one more new tab, new file, new script file. There we entered the program and the previous data is there in the command window. So first line, if you place the CLC, it will clear previous data and it will show the current output only. Okay, now save the file. File name, let it be same. Yeah, now you check the command window graph also. Okay, check the command window. Numerator 100 and coming to the denominator 120 0. So what is the open loop system we are taking? The open loop system we are taking as a 100 by s square plus 20s. For that we are adding a unity feedback and then we are getting the closed loop transfer function is 100 by s square plus 20s plus 100. This is the closed loop transfer function. For the closed loop transfer function, we applied a step input and we need to check the output characteristics. Right? This is the waveform. If we observe, this is a critically damped system. Critically damped system, so we are not having any oscillations. So for this waveform also, we need to observe peak response. Where we are having the peak response, it is we are not having any oscillations, so overshoot will be 0. Peak amplitude greater than 0.997. Peak time greater than 0.8 seconds. And coming to the next one, settling time. Where we are having a settling time. Settling time is 0.583. Settling time is 0.583 seconds. And coming to the next parameter, rise time. Here is the rise time is there. Rise time is 0.336 seconds. And coming to the next parameter, steady state. Need to observe the steady state. So for observing the steady state, here on also final value will be 1. So here also steady state error will be 0. So we are getting final value as a 1. This is the second program output. It is a critically damped system. We are not having any oscillations. Overshoot will be 0. And now we'll see the last program. We'll copy the last program directly from this slide. And let's see. I'm pasting in the script file. So first one will be CLC, and then next we are copying the program. Yeah, this is the last program. Now we'll run this program. We need to save. File name will be okay. Let it be. Yeah, waveform also came. Yeah. Now it is the last case program. We will see the command window. Internal data is there. So numerator we gave as 100, denominator 100, 0. So we are getting a open loop transfer function. We are getting a open loop transfer function 100 by s square plus 100s. 100 by s square plus 100s. It's the open loop transfer function. For that we are giving a unity feedback element, and then we are getting a closed loop transfer function. This is the closed loop transfer function 100 by s square plus 100s plus 100. This is the closed loop transfer function. For the closed loop transfer function, we applied a step input and we need to check the output response. Okay, and this is an overdamped case. Overdamped case means here also we are not having any oscillations. Check the output response. So here also we are not having any oscillations. right? Again, here we need to check all the parameters. What is the peak time, everything. Yeah, peak amplitude is greater than 1. Overshoot, we are not having anything, 0. And peak time is greater than 9 seconds. Next, settling time. Settling time is 3.88 seconds. For the last case, settling time is 3.88 seconds. And coming to the rise time. Rise time is 2.17 seconds. Rise time for the third case is 2.17 seconds. And coming to the steady state, is we need to identify the final value. Yeah, final value is 1. That means steady state error is 0. Steady state error is 0. That means you can get all the values from the graph, or directly you can get in command window also. For that, the command will be step info of system name. What is the system name? SYS1. Close the bracket. Now we'll run the program. Now if we run means graph also will come and the data also directly it will come in command window. We check the command window, already data is there. Yeah, you see numerator, denominator, system open loop transfer function, feedback element, closed loop transfer function, and directly shows the rise time value, settling time, overshoot, peak amplitude, peak time. For all the programs, it will show directly. Now we entered this step info for last program. That's why it's showing the last one. If we enter for the second program also directly, it will come step info of system name SYS1. Run. Already we saved the file. We'll run. We check. Is in second program output. What is the rise time, settling time, peak overshoot, everything. This all data we can identify from the graph and also from the command window also. Okay, this is the data how we are entering, how we are writing the coding part, and how we are simulating and how we are observing the output characteristics. Right. And coming to the conclusion, that is the result. Yeah, this is the program one response. It is an underdamped system. Underdamped system, exponentially decreasing oscillations. We identify what is the rise time, peak overshoot, peak time, amplitude, settling time, final value. In the same way for the second program, that is a critically damped system. For critically damped system also, we check the rise time, settling time, final value. And coming to the third case, is an overdamped system. For the overdamped system also, we verify all the parameters, right? And coming to the result of this one, for the open loop transfer function first case, for the first case, what is the zeta and the omega n values you are getting? 0.51, 10. So 0.5 means it is an underdamped system. In case of underdamped system, we are having exponentially decreasing sinusoidal oscillations. So under this case, what about the rise time? We are getting 0.164 seconds. Peak time is 0.36 seconds. Peak overshoot is 16.3%. Settling time. And here the steady state error is 0. So steady state output will be 1 for the first case. The same way coming to the second case. That means second case, the open loop transfer function is 100 by S into 100 by S square plus 20S. 100 by S square plus 20S. For this, the zeta value and omega n value are getting as 1 and 10. That means 1 is the zeta value. It's in critically damped system. So in critically damped system, we are not having any oscillations. This in critically damped system, we are not having any oscillations. And also we observe the what is the rise time, settling time, steady state output. Okay, this is the second case. It is a critically damped system. And coming to the next case, is the third case. Third case open loop transfer function is 100 by S square plus 100S. So for this system, what about the omega n and zeta value means? Here the zeta value you are getting as a 5 and omega n equal to 10. So it is an greater than 1. So it is an overdamped system. It is an overdamped system. In case of overdamped system also, we are not having any oscillations. Overdamped system also, we are not having any oscillations. So for this overdamped system also, we identified the rise time, settling time, and steady state output. For all the three cases, the steady state error will be 0. And coming to the output, we are getting as a 1. Final value will be 1. Even though steady state error is zero, output is same. But if we observe the rise time, if we are increasing the zeta value, if we are increasing the damping ratio, rise time is increasing. If we observe the waveforms, if we are increasing the damping ratio, automatically rise time is increasing. If the rise time is increasing means the response will be slow. System response becomes slower. Right? Steady state error is zero, but rise time is increasing. Zeta value is increasing, so rise time is increasing. And one more thing, if we are increasing the damping ratio, automatically overshoot is decreasing. So we need to choose a proper value which suitable for both the rise time and overshoot. Based on that, we need to select the proper zeta value. Thank you.